Hello, and welcome to the first video for section 14.5, which covers curvature and normal vectors. In this first video in the section, I'll provide a brief overview of what we're going to talk about in the section, and then get into the first topic, which is curvature. So as an overview, what are we doing here? Our sort of big goal is to develop a complete description of the shape of any curve. So how curvy it is, how much it twists, how does an object move along the curve, things like this. So some things we already have that are going to help us, that are our launching point: tangent vectors and lengths of curves. We're going to need these things. And what we're going to develop is curvature, how fast a curve turns a point. We're going to start getting into that in this video. Normal vectors, these are going to tell us the direction in which a curve is turning. Torsion, which is this other aspect of a curve, which is its twistiness. So this is going to be different from how curvy the curve is, but instead how twisty the curve is. So we're going to have to make sense of exactly what that means later on. We're going to have a nice rigorous definition of it, and we'll get to that later. And then finally, binormal vectors, which are the direction of the twisting. So some things to look forward to there. Like I said, we're going to first start off with curvature. So we want to understand sort of how quickly, how fast a curve turns at any point on the curve. So I'll remind you that an acceleration, so if we're imagining an object moving along this curve as the curve, so the curve is the object's trajectory, remember that an object can accelerate in two different ways. Acceleration can come from a change in speed, if we're accelerating along the trajectory, or if the trajectory is curving, then that is also an acceleration. That's an acceleration due to a change in direction, right? Think about the accelerators that your car has. Of course, you have the pedal accelerator, which changes your speed, but at the same time, you also have a steering wheel. Right? The steering wheel changes your direction, and that's also an acceleration. I'll ask you to remember the examples we did where we were studying just the trajectory of a circle, right? An object moving along just in a circle at a constant rate of speed was accelerating towards the center of the circle, was the idea there. So that also creates a change in, or rather creates an acceleration. Right? Acceleration is change in velocity. Velocity is a vector which carries both a magnitude and a direction. So changing either of those quantities gives us an acceleration. So that's the idea. The curvature comes from this change in direction, right? So if we study the rate at which the car changes direction, that is related to the curvature, right? So for example, a circle, we can discuss its curvature, or just any curve, we can think of its curvature. How does it change direction? So you can think of this, right, like the acceleration that's coming from moving the steering wheel. That's what we're after here with curvature. So how do we get a hold of this quantity? Well, it makes sense to, if we just want to study the change in direction and not change in speed, that we should be working not with the just the tangent vector, but rather the unit tangent vector, right? We strip the tangent vector of all of its magnitude, or rather we force it to have magnitude of 1. We force it to be a unit tangent vector. Remember, that just tells us, the unit tangent vector just tells us the direction in which the object is moving along the curve, and not its speed at all. Remember, we do that by normalizing, by taking its velocity vector and dividing by the magnitude of the velocity, right? This forces it to have unit length. That's sort of the big thing to remember here, is that the magnitude of the unit tangent vector is always 1 at all points along the curve. It just tells us the change, it just tells us the direction that the object is traveling, and not its speed. So we're going to look at this thing, we're going to track this thing as it moves along the curve, and let's just kind of look at an example, well, not maybe a general situation here. So the idea is, I want to see how the unit tangent vector changes over these two curves. Now, how do I compare two curves, right, that might have different parameters? So maybe I move along this curve really slowly and I move along this curve really fast. how do I sort of compare these two curves? The idea is to go back to arc length. Arc length is sort of a normalizing thing between all curves. I can study how the unit tangent vector changes on this first curve as it goes along one arc length or some fraction of an arc length. And same thing over here with the same fraction of arc length. So the idea is, let's say I pick a point here and I can find the unit tangent vector here. And I'm going to call this t of s. So this is some point s along the curve. Right, so let's say this is my unit tangent vector at this point s. So we're thinking of these curves as parameterized by their arc length. So there's t of s. And then let's say I move delta s along the curve, so measured in terms of arc length. So let's say this amount of arc length is my delta s. So a change in arc length. And then I can find my unit tangent vector, should have the same length as this one, unit tangent vector at this point as well. So again, just the direction. It has length 1. And then I can study how did this unit tangent vector, so this will now be t of s plus delta s, so this change in the unit tangent vector. And then if I want, I can plop those two vectors down. Let's see if I can do this really cleverly. Copy that. I don't think I can do this that cleverly. Yeah, there's my, there's t of s. And then I also want to get a hold of t of s plus delta s. That's this one. And I'm going to go ahead and plop them. Yeah, no, this is going to work out all right. I'll put them tail to tail here so that I can investigate their difference. Right, remember that the difference between these two, so this is t of s. And here's t of s plus delta s. Their difference, I want to study how this thing changed, so I want to compute t of s plus delta s minus t of s. This quantity would go from the head of t of s to the head of t of s plus delta s. So this is how it changed over that time frame. So this is the difference there. So notice this changed quite a bit over this delta s arc length. And I'm going to use the same, so I'll use the same point along the curve, let's say t of s here. I guess it doesn't have to be the same point along the curve. But the idea is I want to use the same amount of arc length on this curve. So t of s plus delta s. So, right, so this is going to get sort of flattened out a little bit along this curve, and maybe I end up here. Maybe that's where my t of s plus delta s is for this curve. So t of s, so here's my unit tangent vector here. And then here's my unit tangent vector here. So this is my t of s plus delta s now. And again, I can compare these two vectors. That's not going to quite work out. That's not, yeah. All right, sorry. Trying to do that nicely, but not. I'll just copy this one so it looks like about that. And this one, about that. It's still pointing a little bit there. And then their difference again would be this vector here. This would be my t of s, or rather t of s plus delta s. Minus t of s. So notice this one is much smaller than this one, smaller than the previous curve. So the thing to notice there is over the same change in arc length, so just going along one delta s of arc length in each case, this one didn't change very much, this one did. And just looking at the curves, we can see, oh, yeah, of course, that should happen because this curve is much more curvier. It's changing direction a lot faster than this curve. This curve is much flatter, not changing direction as fast. So you might have guessed it looking at this notation, t of s plus delta s minus t of s. I want to take the limit as delta s goes to 0. That way I'm measuring the curvature right at this point. I want the curvature just at a point. So I want to take delta S to 0, but of course if I do that, well, as long as my curve is sort of continuous or smooth, my difference should go to 0. Right? As long as this vector function is continuous, that quantity would just go to 0, go to the 0 vector. And I don't want that. That's not going to tell me any information. So what I want to do is, just as we've done before, I don't just want the change in the unit tangent vector. I want the change in the unit tangent vector over time. So we really want to consider not just t of s plus delta s minus t of s, but we want to divide that by the amount of time it took. And that's going to sort of not normalize it, but give us our method for understanding the curvature at a single point. So we want to take the limit as delta s goes to 0 of t of s plus delta s minus t of s all over delta s. That's scalar delta s. So that's the idea. This is my curvature, and this is a derivative, right? This looks like a derivative. This is the derivative of t, my unit tangent vector, that vector valued function, with respect to arc lengths. So this is dt ds. So this is going to be an important quantity, but this is a, this is a vector quantity. So curvature is not this dt ds, not this derivative, but rather the magnitude of this derivative. So if we're comparing this one to this one, we have both a direction of the curve, right, direction of the turning, in this case downward, in this case as well downward, but maybe slightly different direction. So we have a direction of the turning, and we have a magnitude of the turning. So curvature is the magnitude of the turning. So curvature is magnitude of dt ds at any point. And we use kappa for this quantity, curvature. So notice this is a scalar. So this quantity we're getting out, how fast it's turning, is a scalar. That makes sense. And then if we pair this with the direction that it's turning, we'll get into that later. That's what the normal vector is. Then we'll have both direction and magnitude of the turning. All right, so just to review what I talked about there. Suppose we have a smooth parameterized curve. Again, I want it to be smooth. Remember, smooth means its derivative is nowhere 0, because then my unit tangent vector is actually defined everywhere. Remember, I have to divide by this magnitude of the unit of the tangent vector. If that's 0, this doesn't exist. So we want our curve to be everywhere, have non-zero derivative. So that's what smooth means. And then we define the curvature as this. So we input an amount of arc length, so input a point on the curve in terms of its arc length, and then evaluate this derivative and evaluate the magnitude of that, and that tells us how curvy it is. That's our curvature. Let's see. So curvature will always be non-negative because it's a magnitude of a vector, and it's a scalar quantity. And the idea here is more curvature, larger value of k at a point indicates a tighter curve. So that's coming from over here. If my vector is bigger, then my magnitude of that will be bigger. I'll have higher curvature here than down here. And then smaller value of k, of course, indicates a flatter curve. Okay, so for this, I'm going to jump to an interactive figure here in Mathematica. So here we have a curve. You can see it in sort of light gray here. This isn't my favorite of all their interactive figures. That's actually why I want to explain it, because it is helpful, but it takes a second to understand what it's saying. So this lighter gray one, this is my curve. And again, what we're looking at here, we're going to look at t of s, so my unit tangent vector. The unit tangent vector, once we've made a little bit of a change in s, so this s plus delta s that I had pictured before. So t of s, right, is right here at the point on the curve. It should be tangent to the curve at every point, so I can kind of check that. Maybe I check it at 1, check it at 2. Yep, it's tangent to the curve at every point. That's my t of s oh, sorry, right here is my t of s. And then t of s plus delta s, so that's this along the arc length. So here is t of s plus delta s as I was drawing before. So between these 2 points, we are measuring the change in the unit tangent vector. And so we can do that by taking this one and moving it to the tail of the other vector, so t of s plus delta s with their tails together. And then as I did before, we look at the change in them, the difference of those 2 vectors going from the head of t of s to the head of t of s plus delta s. So there's that quantity, the change in the 2. And then, of course, we want to divide this by the amount of arc length that we went between those. So that amount of arc length, so let me back up to 1. That's this gray one. So this gray one is my t of s plus delta s minus t of s divided by the change in the arc length. So that's this guy. So it's this vector scaled by the amount of arc length that we actually went by. So that's this. So as I make so there's delta s being 1. It's exactly the same. If I make delta s 0.8, that means this is going to get scaled up by a factor of 25%. This will get scaled up by a factor of 2, right? It's twice as long as that one, right? So that way, as this thing gets smaller, it's actually not going to 0 anymore. And finally, we have that. So here is delta s being 0.01. This is close enough with this curve where it's essentially what this dt ds is. The derivative of t with respect to s is essentially this gray arrow here when we make our delta s small enough. It's a good approximation for it. And so the idea is now we can move along the curve, and at each point we can track that derivative. See how big it is at this point? And that's because we're going around the curve at this point. At this point, the curvature of my curve is very high. We can see that in the magnitude. It's so big here, it's gone off the figure. And now the curvature is getting smaller again, and we're flattening out, and you can see that in the derivative dt ds here. Remember, curvature just keeps track of the magnitude of this thing. So let's just look at the magnitude as we go along this curve, and that's pictured over here. This is the curvature function, right? As you may not have noticed when I define curvature, curvature is a function. It's a function of arc length, so a function of where I am along the curve. So here I start out at this value of s. I can go back to s equals 0. I have this much curvature. Here it's actually pretty high, and that's because we're kind of coming out of a curve here as we start. And let's just see as we move along the curve, this blue line, this is my curvature function, tracks curvature as we move along it. So I'll increment s. Notice it's flattening out here. We're approaching sort of a straightaway. If I were racing my car along this curve, the straightaway would be the perfect point to change my speed rather than my direction. I don't have to be turning my car. I don't have to be using my steering wheel. I can be using all the friction of my wheels to accelerate my object along the trajectory. So that is changing my speed. I could be using this. I like to think of driving a car for these sorts of examples. So here I am. It's a straightaway. I would want to be accelerating, and now we're approaching a curve. My curvature is getting higher, right? And so now I'm going to want to stop accelerating along the curve and start turning, because I need to turn to get around this curve. And there we have it, is a really high curvature. This is going to increment past the peak of the curvature, but the peak of the curvature happened, right around there. That peak of the curvature, and we could actually find that curvature, the peak of the curvature, right? Once we have this curvature function, we could say, take a derivative of it with respect to s again, find when it's 0, and find when this thing is at its maximum curviness. So that's pretty cool that we could use derivatives again to get a hold of that and better understand the curve. Pinpoint, places like maximum curviness. And then we move along, and now we're straightening out again. So this is the idea of curvature. Again, it's dt ds is my encodes both direction of turning and magnitude of turning. Just the magnitude of that is the curvature. It's the magnitude of this vector as we move along the curve. The output of this derivative is a function, curvature, with respect to s. A lot of stuff there. As we work more examples, you'll get more comfortable with it, but hopefully you have the right idea. These are sort of the big takeaways of this. Now, in the next video, we will we'll work through an example where we actually compute the curvature of some curves, and hopefully, yeah, that'll help you better understand. So I'll actually show you how you get a hold of this, because right now, right, we're taking a derivative of t with respect to s. We haven't really done that. All our derivatives have been with respect to the parameter t. So that'll work if we have an arc length parameterization, but if we don't have an arc length parameterization, how do we get a hold of this quantity? That's what I'll talk about in the next video when we work through some examples. I'll see you there.